Assalamu alaikum. Welcome to lecture 12 of data mining. So today we will continue our discussion on frequent pattern mining, and we will focus today we'll focus today on interestingness measures and what those interestingness measures convey regarding the patterns that we have found using our frequent pattern mining algorithms. And we will then move on to some variations and additional categories of applications to which frequent pattern mining can be applied. And then finally, if we have time, we will start with constraint-based item set mining or pattern mining. So today we have kind of a bunch of things to discuss, but most of them are relatively short, but still important concepts. So previously we had discussed the a priori, the FP growth, and the GSP algorithm. So GSP algorithm in particular was used for sequential pattern mining. And as we discussed, it is similar to the a priori algorithm. The only difference is that it has its own definition for supersequence and subsequence. And secondly, it has its own way of generating candidates so that the condition of the candidates being super sequences of the generating item sets or generating sequences is true. So we discussed that last time. So today, as I said, we'll start with interestingness measures for item set mining. So any questions? So we had briefly talked about interestingness measures before as well. So interestingness measures are measures that help us filter out information or patterns that are irrelevant. So these are measures that can be applied on the discovered knowledge, and those patterns or knowledge that satisfy these measures are selected or deemed to be important or actionable for our particular application. You can also think of interestingness measures as evaluation measures. Although in the data mining community, and especially in the context of item set mining, they are more commonly called interestingness measures. So far we had talked about two measures. So we talked about support and we talked about confidence, right? So support of an item set, let's say of an item set AB, is basically defined as the support of so basically you can call it support, but let me write it in another way. It's basically the count of AB in the transactional database divided by N, where N is the total number of transactions in the transactional database. So N okay. So if AB as an item set A and B occurs, let's say some fixed number of times, let's say 100 times, and N is the total number of transactions in a transactional database, let's say 1000, then the support of AB would be 100 divided by 1000 is equal to 0.1. Sometimes we also convert this into percentages. So this would be 10%, which essentially means that 10% of the transactional database contain this item set. So this is an interestingness measure that we used. And we actually utilize this measure within our algorithms, the epi growth algorithm and the a priori algorithm. And we were able to use this threshold to filter out irrelevant or uninteresting item sets earlier in the filtering process or earlier in the mining process. So one way of mining, of course, is you find all possible patterns, and then after you have found all possible patterns, you apply the interestingness measure. The other way is, which is better and preferred, is that you use the interestingness measure, whatever it is, and embed it, or what they call it as push it into the algorithm, so that the algorithm is optimized or with respect to that measure, and it only outputs those measures that are relevant or that satisfy the interestingness measure. Okay? So such algorithms such measures are called pushable. So pushable measures means those measures that can be embedded or be part of the algorithm such that the algorithm becomes more efficient, rather than it being a measure that you apply after the algorithm has found all the possible item sets or pieces of knowledge from the data. So interestingness measure is basically if they're pushable, then that's desirable. Okay. So support was an example of a pushable measure that we used as part of our a priori, epi growth, and other frequent item set mining algorithms. The other measure that we talked about and that applied to rules, which is also another piece of information. Item set is a piece of information, rule is a piece of information. So that is confidence. So A, B. So this is defined as support of AB, the item set AB, divided by support of the item set on the left-hand side. So sometimes you can also say this is probability of B given A. And sometimes this is also written as probability of yeah, I think that's fine. So, but it's okay to look at it in this way. That's the conditional probability of B given A, but you need to be a bit careful because it's not exactly probability in the strictest sense, which is a measure of uncertainty. So this is more of a frequency that you count from the database. So people do write it in this way, but I'm just giving this disclaimer. Sometimes it does lead to some confusion. Okay, I didn't get your question. Quick question, Tapka? Okay. All right. So this is another interestingness measure that we looked at. And if you recall, this measure was not pushed into the algorithm. So we generated the association rules or rules, and then we checked which rules had a confidence greater than some minimum confidence. And then we only kept those rules that were strong. Strong rule means that those rules that have support greater than minimum support and confidence greater than minimum confidence. Okay. The other issue that, so one issue is of course of pushability. The other issue is that what does a measure really tell you about? And there may be different measures. So different measures may tell you different things about the piece of knowledge that you're talking about. So we look at a number of measures for rules and item sets and try to understand what each tells us about and which ones are better and which ones are not good. So let's start with, okay. So let's start with, so one important piece of information is the information regarding correlation. So correlation is basically a statistical concept which implies that if one thing is increasing, the other should also increase. If one is decreasing, the other is also decreasing, meaning that if there's a strong correlation. If there's no correlation, then such a pattern does not exist. And sometimes people also talk about something like causality. So is B caused by A or not? So causality is a stronger concept. And usually from data mining, inferring causal relationships is, I would say, non-trivial and often prone to errors. Because causality is more about cause effect, which thing is caused by something else. And there might be multiple causes for a particular thing. And all of that may not be captured from a particular data mining analysis, but still is an important concept that we need to be aware of. And actually causal inference and causal analysis in active area of research, both in data mining as well as in machine learning and statistics. So, okay. So we talked about the measure confidence. Is confidence a good measure of correlation? So let's look at an example. Just a second. So let's look at this table here, contingency table for the two item sets, or you can think of item set basketball and item set cereal. And of course, B or C, you can say, and not B and not C. Okay. So we have made this contingency table. So 2,000 people, of course, you can say this is a result of a survey of students at a particular university. So 2,000 play cereal and eat cereal, play basketball and eat cereal. And 1,750 eat cereal but do not play basketball. And of course, the total number of people who eat cereal would be the sum, which is 3,750. And similarly, 1,000 are those who do not eat cereal but play basketball, and 250 do neither. And total number of observations or students is 5,000. So from this table, what would be the confidence of basketball cereal? So basketball cereal is the support of basketball and cereal, which is 2,000, divided by total number of observations, which is 5,000. So 2 over 5 is 0.6. Okay. Sorry, 2 over 5 is 0.66. Okay. Or 66%. So this is the confidence for the rule basketball cereal. And of course, the support for this item set is sorry, I missed it. So support is 2,000 over 5,000, which is 0.4, 40%. Okay. And confidence would be what? Support of AB, which is basketball and cereal, divided by the support of cereal, which is 3750. This is 0.66, 66%. So one other thing. So I said confidence basketball serial is support of BC divided by support of B. ठीक है ना? So support हम किस तरह निकालते हैं? It is basically numerator में हमारे पास 2000 है, divided by n which is 5000. And then in the denominator we have 3750 divided by n. So n would cancel out. So we have 2000 divided by 3750, which will give you 66%. Okay? So this is the confidence of this rule. Basketball implies serial. But if you look at the total number of people who eat cereal, so what is the support of cereal? So it was 3750 divided by 5000, which is 75%. Okay? So 75% of the people eat cereal in all. Okay? But when they also play basketball, those who eat cereal is actually reduced to 66. Okay? It's less than 75. So even though the major confidence 0.66 is high, greater than 0.5, this is not indicating correlation. It is just showing the confidence of C given B. It's not showing correlation, meaning that if B increases, C actually decreases. Okay? It's not correlation. So confidence should not be interpreted as correlation. So that's the takeaway from here. Confidence is more closer to the conditional probability rather than correlation. Oftentimes, without even knowing, we say that if the confidence is high, we assume that there is a correlation between the two items in the rule. Okay? So this point clear? So confidence is not a good measure of correlation. Okay? So let's say now if we really wanted to find correlation, so what measure did we have? If you remember, we had studied correlation in data preprocessing as well. And there, when we had nominal attribute values and two of them, we used the chi-square. So you can use the chi-square value to find the correlation. But the problem with chi-square is, and with most algorithms, so chi-square measure is not pushable. Remember, we talked about the idea of pushability. So the idea of pushability is that we should have an algorithm that is based on chi-square, and it only finds those item sets that have a chi-square value greater than some minimum specified chi-square value. So they are they are not as many, or we don't have efficient algorithms for that. So that's why we say they are not. It is not pushable. This measure is not pushable into algorithms. But of course, once you have all the item sets already found, you can compute the chi-square. So chi-square आपको पता है किस तरह निकालते हैं? Contingency table है, observed values हैं, आप expected values भी निकाल लें, फिर उसका square करके sum करके निकाल लें, you get a chi-square value. So another measure that is used is called lift for correlation. So lift is actually related with the notion of independence. So if you talk about joint probability A and B, so when would A and B be equal to, joint probability of A and B be equal to, so for example, probability of A and probability of B, this would be equal when the event A and the event B are uncorrelated actually. And of course, in this case, it will also be independent. ठीक है ना? And of course, this comes from the probability theory as well. So joint is equivalent to the product of the individual events. So if this is the probability, then we can define lift as, so lift of, let's say, a rule A implies B is basically, what would that be? So simply probability of A and B, if you write it in terms of support, it's support of AB. So divided by support of A multiplied by support of B in the denominator. Okay? So this is lift. So again, I've kind of avoided writing it or everything in probability sense because it does causes some confusions in some cases. So, but of course, the motivation comes from probability theory. Okay? So this is lift. So what would lift, if lift is 0, lift is 1. So what does that mean? If lift is 1, so then uncorrelated. And if lift is greater than 1, then you can say they are positively correlated. And if it is less than 1, then it is negatively correlated. So if we look at our example, जो हमारी basketball वाली example थी, so lift of basketball implies serial. So we have support of BC numerator में, denominator में दोनों चीजें हैं आपके पास. Support of B, support of C. Let me write it here. So ऊपर है support of BC. I think basketball serial था 2000. एक second. So 2000 divided by 5000. So support है, ठीक है? Divided by denominator में मेरे पास आ रहा है support of basketball. Basketball की support कितनी थी? I have to look at that. $3,000. So total people who play basketball is 3,000. Total people who eat CD 3,750. ठीक है? So ये 3,000 again support थी 5,000 divide करना into 3750 divided by 5,000. Yes, calculate नहीं किया इसने. यहाँ इस ब्रैकेट में हमने अच्छा ये कैलकुलेट नहीं कर रहा तो अच्छा so you will find that this जी या किसी ने किया कैलकुलेट
जी 8.89
8.8 अच्छा ठीक है ठीक है so it's 8.8 if this is correct then so notice that this is greater than 1 so which means that both basketball and serial are positively correlated which is
0.8
from the contingency table जी 0.8. अच्छा ठीक है. So 0.8 वही ना negative correlated था originally. ठीक है. So 0.8. So which is less than 1. So which means that it is negatively correlated. So the inclusion of basketball actually decreases the observance of serial. ठीक है ना? So lift is a better measure of correlation as opposed to uh, uh, confidence. And of course, chi-square is of course a standard measure for correlation, and you know how to calculate that. But again, lift, of course, there are some algorithms that have modified their approach and they find lift directly, but there are not many. So lift also is difficult to push into an algorithm. So, okay, this is about pushability and correlation. But now let's look into another concept, which does cause problems. I think before that, let me mention some other measures. So let's say, let me talk about a generic 2D contingency table. So let's say मेरे पास ऊपर A है, A, not A, और फिर नीचे B है, ठीक है? And the values for A and B is A, this is B, and then we have not B. The value for this is C, and this is D. And total, of course, A plus B plus C, C plus D is equal to N. क्या हुआ? ठीक है? So एक मैंने generic contingency table बना दिया for some event A and some event B, or for some item A and some item B. ठीक है? You can define actually many measures using this contingency table. दो तीन तो हमने define कर लिए हैं. Lift है, confidence है, support है, chi-square है. ठीक है? So let's look at some other measures, and one measure is called a simple matching coefficient. ठीक है? Which is simply A divided by N. And this measure you have already seen. Actually, you have not seen this. We'll discuss this in clustering for finding the similarity between two objects, the simple matching coefficient. So simple matching coefficient is support, of course, the count A, which is the occurrence of both A and B, divided by total observations. Okay? And then we have another measure called the Jaccard similarity or Jaccard index. This is defined as A divided by A plus B plus C. इसमें D include नहीं होता. So by the way, D है क्या? So D is actually those transactions that do not contain B and that do not contain A. So these are, as we will see, are called null transactions. The transactions that do not contain the item sets of interest in a particular rule, null transactions. So this is Jaccard coefficient, which does not have B in the denominator. And then we have the Sorensen dice, or simply the dice. This is 2A divided by 2A plus B plus C. Okay. By the way, all of these measures you can also write in terms of support and the previous notions that we had, previous notation that we had used. So this is the Sorensen dice. So again, it does not include D. And then I can, in the same sequence, I can write cosine similarity. So this is A divided by SQRT, ठीक है? दो कर लेते हैं. A plus B, A plus C. So this is the cosine similarity. So actually, if you look at these measures very closely, they are, first of all, they have a very nice relationship. You can say one value would be strictly greater than equal to the other value. So let's look at why that is so. So simple matching coefficient, of course, is A over A plus B plus C plus D. ठीक है ना? A divided by A plus B plus C plus D. So you include D in the denominator. So this is going to be the smallest value. ठीक है? If you look at the second one, A over A plus B plus C. So this is the next higher value for any given data set. ठीक है? Of course, greater than or equal to, can be equal to if the null transactions are 0. And then if you look at the third one, उसमें Sorensen dice क्या था? 2A divided by 2A plus B plus C. इसको मैं इस तरह भी लिख सकता हूँ. A divided by 0.5 into A plus B into A plus C. ठीक है? So denominator में it is actually the average of item set A and the item set B का count. Oh sorry, बीच में plus आएगा. ठीक है ना? So 2A plus B plus C. So A plus B, A plus C. And उसका हाफ किया हुआ. What does that mean? कि A का जो काउंट है टोटल, B का जो टोटल काउंट है इसका एवरेज है. So A से न्यूमरेटर A है, नीचे एवरेज से हम डिवाइड कर रहे हैं. So this also would be somewhat less than the previous values because it's the average of the two values. और कोसाइन में ऑफ कोर्स ज्योमेट्रिक आपके पास है. ऊपर A है, नीचे ज्योमेट्रिक मीन है. SQRT of the multiplications of A and B. A plus B, A plus C. ठीक है? So geometric mean, as you know, is always less than or maybe equal to the arithmetic mean. So इसका मतलब है cosine similarity का measure in general will be greater than or equal to the Sorensen dice. ठीक है? So are you following me? So denominator में एक में arithmetic mean था, दूसरे में geometric mean था. और फिर ऊपर वाले दो का रिलेशन में एक में D था, एक में D नहीं था. ठीक है? And of course in general ऊपर वालों से भी ये Sorensen dice और cosine generally बड़े होंगे. So that's one thing that you need to be aware of. So multiple measures may have some relationships that you can derive right from the theory. ठीक है? The other thing that I alluded to was the null invariance. So if you look at the simple matching coefficient in the denominator, it had D. So what is D? D, so number of transactions that do not contain A or B, or A and B. Okay? So it contains none of those. So these are transactions in our transactional database that are irrelevant or do not have any impact on our particular piece of information. Let's say हमने basketball serial की बात करनी है, तो let's say और भी कुछ आपके पास item sets थे. Let's say basketball serial हो गया, maybe some other sports हो गए या hobbies होगी, let's say. But and then there are transactions in which let's say B or C नहीं आ रहे. So to compute the correlation between B and C, we actually do not need those transactions. and actually those transactions could give to misleading result. Let's say मेरे पास दो data sets हैं. Let's say एक data set है जिसमें 1000 transactions हैं और सिर्फ and let's say 900 transactions do not contain AB or BC, जो भी हम consider कर रहे हैं. So 900 transactions are null transactions. So only 100 transactions have the relationship between A and B. So, but if you compute, for example, the simple matching coefficient, वो denominator को 900 भी add करेगा, it will distort the result. Let's say मेरे पास एक और database है, let's say वही वाला 1000 वाला, but उसमें only let's say 200 transactions. Actually, this is probably not a good example. So let's say एक और database में 5000 इसमें transactions हैं, और इसमें let's say आपके पास I would say 3000 do not contain AB. ठीक है? So again, ये जो 3000 number है, it will distort your major simple measuring coefficient because it appears in the denominator. While we are only interested in the 2000 transactions that contain both A and B, if you want to worry about confidence or if you want to worry about correlation. Okay? So we will oftentimes prefer measures that are null invariant, that do not depend on the value D, or that do not depend on the total size of the transactional database, which may contain many null transactions. So such variables, such measures are called null invariant measures. So null invariant, okay? So any measure that is not based on all the transactions in the database or that include the value D is a null invariant measure. ठीक है? So हमने अब काफी measures अभी तक देख लिए हैं. So if you talk about support, is this null invariant? So support of AB, ऊपर आपके पास count आता है of AB divided by n. So it includes n. So this is actually not null invariant. But of course, this is a core measure that we use for finding frequent item sets. So we still use it. So what about confidence? Confidence का formula था, ऊपर support आता था AB का और नीचे support सिर्फ एक item का आता था A. And if you look at the formula, support में ऊपर भी n है, नीचे भी n है. तो दोनों n cut हो जाते हैं. So this is null invariant. So actually confidence has one good property, it is null invariant. But as I said before, it does not tell us about correlation. Okay? It is, you cannot interpret it directly as correlation. ठीक है? So ऊपर जो measures हमने discuss किए थे, jacket, dice, and cosine are all null invariant. Because उन सारों में D नहीं use हो रहा. Invariant. ठीक है? उन सारों में वो D use नहीं होता. All right. So in addition to this, there are other measures as well. For example, एक measure मैं बताऊंगा और maybe there are 2, 3, but मेरे ख्याल से एक ही मैं discuss करूँगा. Book में और भी दिए हैं. There is a measure called all confidence. So for example, let me motivate this. So confidence क्या होता है? A, B का. So you have something support of AB on top and denominator में support of A है. But if you flip it, what is the confidence of B given A? ऊपर वही है सपोर्ट ऑफ ए बी, डिनोमिनेटर में सपोर्ट ऑफ बी है, ठीक है। सो फॉर एनी item set will have something on left hand side and right hand side. So कौन सा confidence ज्यादा होगा? The one for which the denominator is smaller, or the one for which the support of that side is smaller, उसका confidence ज्यादा होगा, ठीक है। So all confidence measure basically returns the minimum confidence of any item set. Let's say आपके पास item set बड़ा मैं कर देता हूँ, A, B, C कर देता हूँ, ठीक है। Although this will make things difficult. दो ही रखता हूँ, A, B. So this is basically the minimum of confidence of A implies B, and confidence of B implies A. ठीक है? Since this is based on confidence, this is of course null invariant. ठीक है? दोनों confidence का minimum हम ले रहे हैं. So maybe आपका item set बड़ा है, वहाँ A, B, C है. इससे कितने rules बनेंगे आपके पास? A implies BC, B implies AC, C implies BC, and then of course combinations AB implies C, AC implies B, and then BC implies A. So in सारे rules का जो भी minimum confidence होगा, that is the one that all confidence would output. ठीक है? So why do we want the minimum? Because we are looking at interesting pieces of knowledge. So if the minimum is greater than our threshold, whatever that is, then we say that that is an interesting piece of information. ठीक है? So any questions? So we have already discussed in a bunch of measures for rules, especially, and for item sets. ठीक है? So finally, so of course you have some idea of which rules are better in general and what are the relationship between those measures, and so some are null invariant, others tell us about conditional probabilities, other tells us about the impact of null invariance, the impact of null transaction. In general, the impact of null transactions is undesirable in measures for item set mining, because you may have multiple transactional databases. एक में null invariance ज़्यादा होंगे और एक में null transactions ज़्यादा होंगे, दूसरे में कम होंगे, तो your answer would be impacted by that factor. So we don't want that to happen. All right. So finally, there are a couple of more measures which is sometimes recommended if you don't want to worry about the other measures. So one is called the Kulczynski index or coefficient. So this is simply the average of the two possible confidences. Rather than the minimum, it's the average. So if you have, so it is basically 0.5 into confidence. So, so this is the average of the two possible rules and their confidences, and this is called the Kulczynski index or coefficient. All right. So the Kulzinski index is essentially the average or the mean of the two confidences. So is this measure null invariant or not? So it is null invariant. It does not depend on the total number of transactions. Confidence does not depend on the total number of transactions. The total number of transactions n is cancelled out. Okay? So as such, you can use this measure to compare the frequency, the confidence of rules that are found from different transactional databases of different sizes. Okay? So along with Kuczynski index, we oftentimes use another measure that tells us the direction of the imbalance among the two possible rules for an item set AB. So AB has two possible rules, B implies A or A implies B. So that is called the imbalance ratio. So imbalance ratio for AB. So basically this is equal to the absolute value support of A, the left-hand side, minus the support of the right-hand side B, the absolute value. So it might be positive, it might be negative, we take the absolute value, divided by the support of A plus the support of B minus the support of AB. So this is the normalizing factor in the denominator. So this value would give you a number between 0 and 1, of course. The higher the number, you will say that the higher the imbalance between the two possible options for this rule. Okay? So दो possible options क्या आती हैं? B implies A or A implies B. So if this value is high, then it means that maybe one value is significantly different from the other value. And the first one, Kulzinski, gives you an average of the two confidences. Okay? And this average has been shown to be, for most practical cases, more consistent with correlation than the simple confidence. ठीक है? Remember, हमने पहले confidence निकाला था basketball serial का. वो confidence 0.66 तो आ रहा था, but actually basketball and serial were negatively correlated. उसका उल्टा हम निकालते serial और basketball, तो हमारे पास एक और confidence आता है, तो दोनों के average लेते, that average would have been less than 0.5. So that would have been a better measure of correlation than just simple confidence. ठीक है? So Kulzinski and imbalance ratio, if you want to restrict yourself to just a few measures, then you can use these two measures. Kulzinski would give a good idea of the confidence as well as some idea of the correlation. And imbalance ratio would tell you how different the two possible rules are in the item set that you're studying. ठीक है? Any questions? Of course, there are other measures as well. I won't discuss them in detail. One is called coherence. I think there is also something called that oil confidence. I think discuss kar liya tha. Anyway, so there are many other measures, but it's not that important to know all of those measures, but it's important that each measure can convey something different, and we need to be aware of that and be able to recognize differences in measures while we are evaluating our patterns. And the other concept that I highlighted through this was the concept of pushability. So a measure that can be pushed into an algorithm would make the algorithm more efficient. So, so that is also important. And then, of course, the issue of null invariance. So we like our measures to be null invariant as well. So with that, I think I will conclude this section. And by the way, this is was chapter, I think, 5 of your textbook by hand, which is basic item set mining. So we'll now quickly discuss some topics from chapter 6, which is on advanced topics in item set mining. We had already discussed one topic that was out of this chapter, which is the sequential pattern mining, which is from another book. So now let's talk about some other concepts, of course, within item set and pattern mining. So, okay, this is. So we'll talk about two topics from this chapter, which has some other topics as well. We won't discuss those topics in detail. We'll talk about, first of all, some other terminology and variations, which is multi-level item set mining or multidimensional item set mining or relational item set mining. And then we'll talk about constrained item set mining. And this constrained mining, of course, is a general concept that can be applied to other tasks as well. For example, constrained clustering and constrained outlier analysis and so on. So we won't talk about some of the other topics like mining high dimensional data and so on. Okay. So if you remember, we talked about concept hierarchies at the end of data preprocessing, and concept hierarchies are quite useful in understanding information because they often represent levels of granularity of our data set. And as part of our item set mining problem, we can also take advantage of concept hierarchies to get a better idea of our item sets and maybe reduce the number of item sets that we want to analyze. So for example, there's an example given here regarding, let's say, if you talk about a grocery store, if you go to the grocery store, you might have a category called milk. So within milk, there might be multiple types of milk. So you might have full cream milk, 2% milk, 1% milk, fat-free milk. And let's say within full cream milk, you might have different brands, maybe Allpers and Milk Pack and I don't know, A and so on. So there's a hierarchy. So you have milk. Under milk, you have various types of milk. For example, 2% milk or 1% milk. And under 2% milk, you might have, let's say, a brand by Allper. And maybe even you can go down under Allper, you might have a packing for 1 liter and 1.5 liter and so on. So now the question is, if you are mining at a particular level, let's say you're mining at the level of milk, tea, bread, and so on. And another level is you're mining at the level of, let's say, 1% milk by Allpur and of size 1.5. And similarly for bread, I don't know, 400-gram bread by Dawn, by whatever. So which items are you going to find in greater quantities at the higher level or at the lower level for a particular grocery store? So obviously at a higher level, you will find more transactions because everything from below is aggregated up there. So if someone bought a 2% milk and someone bought a 1% milk, that means there are 2 milk items that are sold. But there were 2%, there was 1%. So everything gets aggregated. So the support of item sets at a higher level would generally be higher, and the support of item set at a lower level would be generally lower. So you can use this guide to, you can say, interactively mine item sets in your data set. So maybe you can start with a higher level item sets and maybe put a higher threshold to find some of the interesting item sets at the higher level. Maybe you find that milk and bread are sold together. So maybe you found that to be frequent. Let's say you use the threshold of, let's say, 10%. And then you can now drill down and find which bread and milk were sold together. So maybe you find out 2% milk and Dawn bread were sold together most frequently. Of course, this support would be less or equal to 10%. It would be generally less. So let's say it's 3%, but still you are doing it in an interactive fashion, multi-level analysis of your data set. Rather than finding, let's say, many patterns at the higher level, which might be irrelevant, or no patterns at the lower level. You start with some patterns at the top level, then drill down into the lower level. Okay? So the takeaway, of course, here is if you're doing multi-level association mining or item set mining, at the higher level, you will generally use a higher support threshold or minimum support threshold. And at the lower level, use a lower minimum support threshold. Okay? And of course, you can do this in an interactive, iterative fashion. Okay? Of course, you can do cross level also. So maybe you are interested in milk, which is one level, and maybe a specific type of bread, let's say brown bread. So you can do that as well. So generally, you will select different thresholds at different level, and you will try to keep them flexible so that you can find more interesting items from your data set. And there are some techniques out there that can work with multiple thresholds, minimum support thresholds. So we didn't discuss those techniques in this course, but there are some techniques out there that you can you can give it multiple thresholds. For example, 2%, 3%, 4%, and 5% together at once. And it can systematically filter out item sets that are important to you. Okay, so generally those algorithms are called multiple support item set mining. So it's a slight variation of your A priori and FP growth algorithm. So we did not discuss those in detail in this course. So next, let's look at multidimensional, and this will lead to our relational concept. So far, so we had talked about multi-level. So now let's talk about multi-dimensional mining or item set mining. So dimension here means an important, you can say, feature or factor, or you can say attribute. Okay? This is dimension that is commonly used in statistics as well as in data warehousing, for example. So far we had talked about the example of the retail store where we buy something. So in that case, our dimension was actually just one, buy. Buy, let's say milk, and let's say buy bread, and let's say buy, let's say whatever, tea, for example. So this was our item set that we were looking at. We did not drive buy explicitly there because all, you can say, dimensions, or we can also say predicates, were the same. Okay? So in this case, it's not multidimensional item set mining. But in general, you can have multidimensional item set mining. For example, you can have so you can have item sets like actually, the notation may not be that good that I wrote before. So let's say gender is one predicate or dimension, M, and then let's say by, let's say, I don't know, by, let's say, computer, and then let's say again you have by, let's say, printer. So now this is an example of a multi-dimensional item set, which we also sometimes called a predicate set. So multi-dimensional item set, which is also called a predicate set. Okay. So now we have more than one dimension. So you have the gender dimension and you have the bi dimension. So gender, male or female, and there are two predicates of bi. So this set is called a predicate set, not the item set, because now it's a combination of the predicate and the value. Okay. So so many of our databases do have multiple attributes or features or predicates or dimensions. So you can think of all our tabular or relational DBs have multiple columns. So let's say if you talk about the student database that we had been referring to many times in this course, the student database at LUMS, so you can have name, for example, as an attribute. You can have age as an attribute. We can have gender as an attribute. We can have GPA as an attribute. We can have, let's say, first, let's say, preference for, let's say, sports. So second, sports. So you can have a database like this. So ये आपके columns हैं और फिर नीचे आपके पास information है. So using this notion of multi-dimensional item sets or predicate sets, you can actually mine such databases as well and find frequently occurring predicate sets. Okay? So in such a case, you might be able to find interesting frequent patterns like maybe age is, of course, to apply item set mining effectively, you probably have to discretize continuous value. So let's say age को आपने discretize कर दिया हुआ है. So let's say age, let's say in the bracket 18 to 20, and let's say gender is female, and then let's say plays, first play or first sports is, let's say, basketball. Maybe this item set or predicate set is frequent. While if you, let's say, switch the gender to male, it is not found to be frequent. So things like that can be found from relational databases. Okay. So, so now the question is, can we apply our previous algorithms that we had studied before to mine such kind of predicate sets? The answer is actually yes, and with little modification. One way is that you convert all the attributes in your data set into one of k, use one of k encoding to convert them. So for example, so let's say gender hai. So gender is equal to m become one attribute, and gender is equal to f become another attribute. Okay. And for any particular student, you either have 1 there and 0 there, or 0 there and 1 there. Okay. So now GM and GF is considered like an item, a binary item, just like someone buys or does not buy. Okay. And then you can apply your algorithm, a priori algorithm, directly on it. And of course, if you have an attribute with multiple values, then you define multiple columns with 1 in one place and zeros in all the other places for any given transaction. But there are some other things that you need to be aware of. So for example, when you're generating new item sets, or let's say जैसे a priori algorithm candidates generate करते हैं, तो let's say आपके पास GM एक item है और predicate item है, predicate set कह लें, predicate item कह लें, ठीक है? Then you cannot have a predicate set that has two G's in it. So this is not a legal candidate item set, or it's not even a legal predicate item set, because in any given row of your database, you would not have two values of gender. They would either be M or they would either be F. And obviously, both of them occurring in the same transaction would have a count of 0 for all the database. So इसको generate करने की जरूरत ही नहीं है. Of course, you may have different combination, M and let's say age is equal to 1820. So that is legal. There's no issue with that. Okay. So some additional bookkeeping is required, but you can still apply your existing algorithms for finding frequent predicate sets. So by the way, इसमें वही notation use होती है. The K predicate set is an predicate set with K predicates. So जो ऊपर हमने example दी, it has two predicates. So this is a two predicate set. So this is basically a two predicate set. And of course, your algorithm like a priori will proceed in the same fashion. You first generate the candidate one predicate set, you count them, then you find the frequent one predicate set, From the frequent one predicate set, you generate the candidate two predicate sets. From the candidate two predicate sets, you find the frequent two predicate sets. From the frequent two to candidate three, and so on, until you have found the longest predicate set in your data set. So I think that is pretty much all for today. I think I've spoken continuously for quite a while now. So any questions? Any questions? So we have just one important topic left that would take about 30 minutes more on item set mining, and then we'll move on to some classification and then to clustering. So in the next lecture, do you want me to continue with the content, or should it be a review type of lecture? Because we have a midterm exam on Friday. Okay, so we will have then a review session on Thursday. The review would, of course, be just going quickly over the content that we have covered. And then if you have specific questions, we will answer those during the session. Okay, so please come prepared with specific questions, and we will discuss those during the time slot on Thursday. So your exam, midterm exam, is on Friday at 6:30 on campus.